In this program, we'll look at some of the inspirational and amazing properties of light. Light is produced in a number of ways. Most of the light we see comes from anything which is extremely hot. In a fire, we see a range of colors because different parts of it are at different temperatures. You can measure the temperature of an object by its color. This is red hot, which in fact is quite cool. This is yellow hot, which is hotter than red. This molten gold is also yellow hot. A candle flame is hotter than yellow light, which is why the color is closer to white. A light globe filament is hotter again than candle light. It's made from tungsten, so it doesn't melt. The person in the foreground is using a welder, while in the background, the other person is using an angle grinder. Notice the difference in the color of the sparks, which are small grains of hot metal. The sparks from the angle grinder are yellow hot. The welder has to be hot enough to melt iron, so the sparks which it makes are white hot. The sun is even hotter than molten iron, and we see sunlight as white. Most stars are even hotter. In fact, some are blue hot. Apart from heat, there are entirely different ways to produce light. When atomic particles fly out from the sun and hit the atmosphere, they stir up electrons to give off light. This produces the magical aurora known as the northern and southern lights. A fluorescent light works on the same principle, except it uses electricity to knock electrons about. Light is produced when the electrons in an atom are disturbed. Electrons are little bits of electricity making up the outside of the atom. When they are disturbed, they produce a pulse of electromagnetism. This pulse is known as a photon and is the smallest piece of light you can have. When countless billions of photons head from the sun to Earth, they travel as waves. Let's look now at how light travels. Why does light go through some objects and not through others? Here, there is no object traveling along the line, only movement. We call this a wave. Photons are also waves. When photons of light come to the electrons in glass, they vibrate the electrons, causing a wave. So at the other side of the glass, the vibration of electrons produces a photon. Nothing is passed through except the movement. Light can pass straight through glass, which is faultless. It's transparent. If the glass has been roughened or etched, the photon still passes through, but it becomes scattered, going off in different directions. We call this translucent. Milk makes water translucent because millions of tiny drops of oil in the milk scatter the light in different directions. In metals, there are a lot of electrons wandering about freely, so the vibration does not get passed through the metal. Instead, new photons are produced and sent back out. So light does not pass through metals, but is always reflected by them. This ancient Egyptian mirror is made from smooth, polished metal. If the metal is bent, the image is distorted. Materials which can conduct electricity will also reflect light. When we join the wires in this electric circuit, the light goes on. When we test to see if electricity will go through the glass, it doesn't, nor will it go through the water. But it does flow through the metallic spoon, which also reflects light. And the reverse is true. If a material won't let electricity through, it will let light through. If light hits glass or water at an angle, it will bend. This is called refraction. Cut crystal glass has many faces at different angles, and so refracts light off in many different directions. This pen appears to bend when it is in water due to refraction. When light hits a curved object like this glass, it changes the image. In this case, the curved glass focuses the light to a point. If glass is ground accurately enough, it can produce accurate images and be used in a camera. If you've held a lens up like this, you'll have noticed that the image is upside down. In the camera, the picture is upside down. Our eye works just like a camera lens, and in fact the image on the back of our eyes is upside down, but our brain corrects for it. If you dive underwater and then look up, you'll find that at certain angles you can't see out. At certain angles, the surface becomes a mirror. This is known as total internal reflection. The light becomes trapped inside and can't get out. This even happens inside a jet of water with this laser beam. The laser light gets trapped inside the stream and can travel along it even as it bends. This happens with any transparent rod. The light is internally reflected off the sides and cannot escape until it reaches the end of the rod. This is how we can send light messages down an optical fiber. Like waves on the ocean, white light is made up of many different wavelengths. When we take a slit of sunlight and pass it through a triangular prism, it will split up the different colors. This is because there are many different wavelengths in white light. Our eye sees each wavelength as a different color. Like the prism, a crystal can separate the different wavelengths so that we can see them as colors. This display of colors is called a spectrum. This is how raindrops produce a rainbow. Rainbows only occur when you have sunlight and rain and when the light is behind you. You can make your own rainbow at any time it is sunny with a garden hose and the sun behind you. A rainbow will go the full 360 degrees if you can get up high enough. There is always a second rainbow, but sometimes it is very faint. The rainbow stands out the most if the background is dark. If we look at a compact disc, we can also see a spectrum of colors. This is because the shiny surface has lots of closely spaced fine lines which produce different colors at different angles. This is called diffraction. If scientists want to examine light, they use a special mirror called a diffraction grating. This has hundreds of thousands of very fine lines etched into it. These glasses also have millions of lines on them, and they too produce colors. This shell has no colors of its own, but it produces a rainbow because it is made up of many thin, clear layers. A thin film of oil on water also produces colors of light. Any clear film, if it is thin enough, will separate light. This film is made of soap and water. So, if we mix the various colors back again, do we get white light? If we mix red, green, and blue lights, do we get white light? We can test this by using 3 projectors, each with a different colored filter. Red and green together give yellow. Blue and green together give cyan. And all 3 together give you white light. Up the top, you'll see the red and blue make magenta. Color television produces all its colors by mixing red, green, and blue. If you take a magnifying glass or a camera lens and look more closely at a white spot, you'll find the 3 colors. When you look through polarizing sunglasses, they cut the glare from water and let you see what's on the bottom. If we watch the photons coming toward us from this atom, we can see that some of them are vibrating up and down, and others are vibrating sideways. This one is up and down, and this one sideways. We can represent the photons like this. Polarizing sunglasses are like a wire grate. The grate can allow light to go through, or it can stop it, depending on which way it's turned. These are polarizing filters. The first filter selects out the light going in one direction. This light can now pass through the second polarizing filter. But once the second filter is turned, the remaining light cannot get through. This is called crossing the filters. Some of the light around us is polarized, such as the reflections off glass or water. We can only detect this by looking at it through a polarized filter and turning it. A liquid crystal display, or LCD screen, gives off polarized light. And if you wear your sunglasses sideways, you'll have trouble reading your LCD watch. You can have a lot of fun experimenting with this yourself and finding out where the light is polarized. Try reflections off transparent objects such as glass, water, or a glossy desk or brochure. Then try reflections from a mirror, dull metal, or paper, or a painted surface. You could try smog or smoky air, or cloudy water. If you hold a polarizing filter up to the blue sky and rotate it, you'll see that the skylight is polarized. The direction of the polarization depends on the position of the sun. Where the sunglasses are the darkest, the nose will point up to the sun. In fact, ants and crabs have built-in polarizing filters or glasses in their eyes and navigate by finding out which part of the sky is polarized. Imagine you're an ant. You wake up in the morning and your polarizing sunglasses can tell you which direction the sun is in, even if it's hidden by trees. In photography, a polarizing filter is a good way to make the clouds stand out by making the blue sky darker. We've used the crossing of polarized filters to tell which light is polarized. Now let's look at some magic when we cross two filters. These three tanks all contain different amounts of sugar dissolved in them. Sugar in solution can actually rotate polarized light. So, if we put the tanks between two crossed filters, then they will rotate the light enough to get through the second filter. Cellophane between crossed polarizing filters does the same. If we take a piece of plastic, such as plexiglass, and stretch it out or squeeze it, it will affect light passing through. Engineers can use this to test the stress in a model bridge. If we squeeze a plexiglass model of a bridge between crossed polarizing filters, parts under most stress will produce the strongest colors. If we look at a plastic cup, we can see where there is still stress left from the manufacturing process. And we can also see the stress points in a car window where it was cooled with air jets in manufacturing. All life on Earth depends on light, carrying energy right to the depths of our oceans. The wonderful and fantastic properties of light are part of the miracles of nature. Light intrigues us, fascinates us, and invites us to explore more.